Good morning, students. In this video, we are going to study about some important concepts of the chapter gravitation. Orbital velocity. So what is orbital velocity? This is a velocity required by a satellite to put the satellite into its orbit around the Earth. So to solve the expression for orbital velocity, let capital M be the mass of the Earth, capital R be the radius of the Earth, small m means the mass of the satellite, V0 is the orbital velocity of the satellite with which the satellite put into its orbit around the Earth, and here h is the height of the satellite above Earth's surface. So according to the law of gravitation, we know that the force F is equal to capital G, capital M into small m divided by R plus H whole square. So what is R plus H here? R plus H is the orbital radius of the satellite. Here R denotes the radius of the Earth and H is the height of the satellite above the Earth's surface. So we know that for any object or for a satellite to be in a circular motion, there is a requirement of the centripetal force. So the centripetal force required by the satellite to keep it in its orbit is given by F is equal to mv0 square divided by R plus H. We know the formula of the centripetal forces. F is equal to mv square over R. In this case, here velocity V is equal to orbital velocity of the satellite. So we use the symbol V0 square, and for the distance R, here the distance is equal to R plus H. So we replace the R with R plus H. To put the satellite into its orbit around the Earth, there is a requirement of the orbital velocity. Orbital velocity make the satellites to move in its orbit around the Earth in a circular path. So hence there is a one force that is required to make the object revolving in a circular path, and that force is a centripetal force. But along with the centripetal force, there is also gravitational pull of the Earth. So in order to make the satellite revolving with the orbital velocity around the Earth, both these forces must be in equilibrium, or we can say that both these forces must be balanced with each other. So for equilibrium, so both the forces are equal to each other, and from this, after solving the equation, we get the equation for V0 square. So V0 square is equal to Gm divided by R plus H. So finally, we get the final result for the orbital velocity, that is a value for the V0 is equal to under root of Gm divided by R plus H. We can also write this equation in the form of the small g, that is when we take into consideration the acceleration due to gravity on the Earth's surface. We know that the value of small g on Earth's surface is equal to capital G into capital M divided by R square. Here capital M and R is the mass and the radius of the Earth. So on rearranging the terms, we get the new equation Gm is equal to small g into R square. Now put the value of the Gm in the previous equation, that is the equation of orbital velocity. After putting this value, we get the new equation for the orbital velocity, that orbital velocity is equal to under root of small g R square divided by R plus H, and on rearranging the terms, we get R into under root of G divided by R plus H. So this is the another relation for orbital velocity in terms of acceleration due to gravity on the Earth's surface. Now we are looking next for the special case. Special case when we assume or when this happens, like when satellite revolves close to the surface of the Earth. It means that for this case h is equal to 0. So we can take h is equal to 0 in this equation. So when h is equal to 0, we get some another equation. So the another equation is v naught is equal to under root of gr. So this is the equation for the orbital velocity when h is equal to 0, or we can say that when satellite revolves close to the surface of the Earth. So put the value of the g. We know that the value of the small g, that is 9.8 meter per second square. We also know about the radius of the Earth, that is 6.4 into 10 raised to power 6 meter. After putting these values, we get the result of the orbital velocity in numeric value, that is 7.92 in 92 kilometer per second. There are some important points that we understood from the equation number 1, and this one is the equation number 1. The first point is, from the equation number 1 we can easily see that it is independent of the mass of the satellite. It means that in this equation there is no role of the mass of the satellite. And second, that the orbital velocity of the satellite decreases with increase in the radius of the orbit, and also decreases with increase in the height of the satellite. Because, and when if we look at the equation number 1, the r and the h, both these terms are in denominator and they vary inversely with respect to the orbital velocity. So hence orbital velocity get decreases if there is increase in the radius of the orbit and also increase in the height of the satellite. Also the third point, that orbital velocity depends on the mass and the radius of the planet, which is also shown in the equation number 1, that orbital velocity depends upon the capital M, that is the mass of the Earth, and capital R, that is the radius of the Earth. So this point is also very much clear, that orbital velocity depends on the mass and radius of the planet about which the satellite revolves. Next topic is a relation between orbital velocity and escape velocity. We know that the escape velocity of a body from the Earth is given by relation VE is equal to under root of 2gr. Here the subscript E signifies escape velocity, and the orbital velocity of the satellite revolving close to the Earth's surface is given by V naught is equal to under root of gr. Divide both the terms, and after this we get the answer, that is equal to under root 2. Cross multiply these terms, we get the answer of the escape velocity in terms of the orbital velocity, that is VE is equal to under root of 2V naught. So hence we can say that escape velocity of a body from the Earth's surface is under root 2 times its velocity in a circular orbit just above the Earth's surface. So the next topic is time period of satellite. It means that time taken by a satellite to complete one revolution around the Earth. So it means the time taken by a satellite to revolve around the circumference of the orbit with its orbital velocity. So formula for the time period of satellite is equal to circumference of the orbit divided by orbital velocity. We know the formula for the circumference of a circle is 2 2 pi r, but in this case here in place of r we are using r plus h, because r plus h is the orbital radius of the satellite. So we get 2 pi into r plus h divided by v naught. Calculate the value of the time period mathematically, we know the formula for the orbital velocity. V naught is equal to under root of gm divided by r plus h. So in the formula of the time period, put the value of the orbital velocity and solve it. We get a result 2 pi under root of r plus h whole cube divided by gm. And we aware about the formula of the acceleration due to gravity on Earth's surface. G is equal to gm divided by r square. Again rearrange the terms and get the value of the gm, put the value of the gm, and we get the equation T is equal to 2 pi under root of r plus h whole cube divided by gr square. Now for the special case when h is equal to 0, which means that when satellite revolve close to the earth's surface. So for this case the time period is equal to 2 pi under root of r cube divided by gm, because in this case we take h is equal to 0. So after solving this we get 2 pi under root of r over g, because we know gm is equal to gr square. So put the value of the gm as gr square, r square and r cube get cancelled out, and we get finally 2m under root of r upon g. Now we know the value of the small g and the capital R. So put the value. So time period capital T in numeric form is equal to 5078 seconds, and in minutes this is equal to 84.6 minutes. Similarly, we can find the expression for the height of a satellite above the Earth's surface. So for height of the satellite, take this equation of the time period as equation number 2, squaring both sides of this equation. After squaring, we get t square is equal to 4 pi square, under root get cancel out or resolve, and r plus h cube divided by gr square. Rearrange the terms, cross multiply them, we get r plus h whole cube is equal to t square r square g divided by 4 pi square. Now take the square root and we get the value for the r plus h. After getting the value for the r plus h, take the r on the another side and we get the answer for the height of the satellite. So this equation specify the height of the satellite, and the height of the satellite is given by t square r square g divided by 4 pi square. And for this we take this as a 1 upon 3. Here 1 upon 3 arises because it arises by taking the cube root on the both sides of the previous equation, and this term is get minus, that is minus r. So this is a result for the height of the satellite. Hope you get this concept very well. Thank you for watching this. Have a good day.